Hi, my name is Ray Gonzalez. If you're a cybersecurity professional or even considering getting into the field, the one salient thought at the back of your mind is how would AI affect your future career prospects? With the rise of AI in cybersecurity, the truth is this. If you want to keep your job, you cannot just be a user of SOC-based AI tools. You have to be a master. So, what is a cybersecurity AI master? It's a professional who doesn't just click and consume outputs, but one who can configure, guide, and corral AI agents. A cybersecurity master understands the functional components of these systems, the prompts, the guardrails, data formatting, and the overall architecture, and uses that knowledge to produce comprehensive, evidence-driven incident reports with actionable recommendations. In this video, you'll see how an understanding of the agent's design makes you a more effective SOC analyst, someone who doesn't just use AI for investigations, but actually shapes it to deliver validated results. Are you ready to boost your career prospects? Then let's get started. First, I'll give you a high-level overview of the agent's operational environment. Then we'll dive into a demo that traces the full process, from the moment the user submits a request to the delivery of the final incident report. I begin with the operational environment because this is what makes the agent real. The agent doesn't live in a vacuum. It works within the SOC ecosystem, pulling data from SIM and log sources, and feeding that data into downstream systems, such as incident reporting platforms like Microsoft Sentinel's Incident Hub, ticketing systems like ServiceNow or Jira, and SOAR applications like Cortex XOR or Splunk SOAR. By understanding how the agent fits into the broader SOC workflow, you'll see how you can guide it to produce higher quality, evidence-backed results. As you can see in the diagram, the agent works with telemetry stored in a log analytics workspace. That data comes from Windows virtual machines, which are monitored by Microsoft Defender for Endpoint. The agent interfaces with log analytics and OpenAI to build KQL queries for analysis and generate reports of its findings. All of these applications and services run on Azure's cloud platform. So let's begin by giving a short walkthrough of what the agent does. After clicking the Run button, the agent responds with the following question. Agentic SOC Analyst at your service, what would you like to investigate? We will now type in our request. I'm concerned of some unauthorized person may have been trying to log into a device Walnet within the past week. Can you investigate? The agent responds with deciding log parameters based on the user request. It then displays its understanding of the user's request by giving a description of its intended search parameters, threat hunt context, and rationale by listing its intended tables and fields that it's going to use during the investigation. Next, it gives the rationale for the table name, saying, since the user asked about logging attempts on device Walnet, it writes, device logging captures login activity, local and remote logons. It includes fields for timestamp, account, device action type, login success or failure, remote IP, and remote device, which are necessary to determine unauthorized attempts and sources. So we can see here, this is the rationale. Next, because we asked for a time range of 1 week, it says that the time range is set to 168 hours, 7 days, because the user specified that the incident occurred within the past week. Next, it presents a notification that it is validating the chosen tables and fields to ensure that they comply with the parameters configured in the guardrail component. See that here. The agent's choice of tables and fields is an important configuration component to guide the agent, and we'll discuss this in detail later in the video. Next, the agent gives us the query that it constructed in KQL, and it builds its threat hunt prompt instructions. The agent then finally gives the models that could be used and their cost and token count, and it tells us that it intends to use GTP 5 mini to do this investigation. We hit enter to confirm its choice, and then the agent starts its threat hunt. It's going to take a few seconds. Now let's take a closer look at the 4 potential threats the agent identified during its analysis. As you review these findings, you'll start noticing a common pattern. Each one of them relates to logon activity. Every threat is mapped to its corresponding MITRE attack technique, along with a short description explaining the behavior. The agent then presents the supporting evidence. The relevant log lines from the Log Analytics workspace, followed by indicators of compromise, descriptive tags, and recommendations. Finally, the agent summarizes its assessment in a concise notes section, giving you an overall sense of risk and context. Let's focus on threat number 2 in more detail. For this finding, the agent assigned a high confidence level. The title describes it as Sustained Targeted Administrator Login Attempts from IP address 50.188.96.138. In the description, the agent highlights multiple login attempts occurring over a 3-hour window from 21:25 to 23:40. The pattern suggests a deliberate, focused attempt to compromise a high-value account, specifically the administrator account. This type of attack is consistent with password guessing or brute force activity. The agent links this activity to the MITRE attack technique T1110 credential access. Evidence of brute force activity is shown via the log lines, which all display logon failed status. The indicators of compromise include the external IP address, multiple timestamps showing repeated login attempts, and user names, administrator, and a malformed unreadable account name. In the notes section, the agent reinforces the heightened risk associated with targeting the administrator account, emphasizing that this behavior represents a serious attempt to gain privileged access. Now that you've seen what the agent can do, how it identifies threats, analyzes log data, and presents its findings, let's take this a step further. So how does the agent know what to look for? How does it appear to think like an experienced threat hunter, identifying key tables, fields, and timeframes relevant to each investigation? The answer lies in its configuration. The agent's performance is not random or improvised. It is directed by four key components that define its analytical logic and operational boundaries: the system prompt, the user prompt, the guardrails, and contextual tuning. The system prompt is the agent's rulebook. It defines its investigative mindset, analyst structure, and reporting standards, ensuring the agent always responds like a disciplined cybersecurity analyst. The user prompt acts as a human-to-AI translator. It converts your natural language requests into clear analytical directives, telling the agent which tables to search, what data to analyze, and what investigative goal to pursue. The guardrails serve as the agent's safety net. They enforce the operational boundaries, keeping the agent within approved data sources, preventing hallucinations, maintaining accuracy, compliance, and cost control. And finally, contextual tuning. This isn't a Python module, but a guiding and foundational framework that represents your professional judgment and an analytical mindset. It refines how the agent interprets each investigation, keeping its focus aligned with real-world threat context and your expertise. Together, these four components transform the agent from a passive AI tool into an intelligent SOC assistant, capable of producing context-appropriate, structured data queries that lead to accurate, data-driven investigations. Now let's take a closer look at our first configuration element, prompts, the instructions that shape how the agent interprets your intent and executes its investigation. Unlike a human analyst, the AI doesn't inherently know its role or responsibilities. It must be explicitly told who it is, what it's analyzing, and how it should respond. These foundational instructions are defined through the system prompt, located in the prompt management Python module, and stored in the variable system_prompt_threat_hunt. Here you can see specific instructions regarding the agent role. For example, you are a cybersecurity threat hunting AI trained to support SOC analysts. You're expected to accurately interpret logs from a variety of sources, including device process events, device network events, device logon events, and other tables. You're expected to map MITRE attack techniques and sub-techniques. We also give it instructions as it relates to the tone of its reply. It should be concise and direct, evidence-based, and replying using structured JSON data. Finally, we tell it what to avoid. It should avoid hallucinations, should avoid vague summaries, and it should avoid explaining basic security concepts unless explicitly asked by the user. Now that we've told the agent who it is and what its responsibilities are, let's explain how the prompt parameter component tells the agent what is the appropriate target log table to query based on the user's request. We'll be using our example of the brute force login attack on the VM Walnet to do this. After the user submits the following request, I'm concerned that some unauthorized person may have been trying to log onto the device Walnet within the past week. Can you investigate? The agent runs the function getQueryContext in the executor Python module. This function populates system message with configuration details via the system prompt tool selection variable that tells the AI which log tables and fields it should use. Now that the configuration details are loaded, the agent makes a call to OpenAI to begin creating the KQL query that will be used for the investigation. The tools equal prompt management tools parameter is another very important configuration component. It gives context and guidelines to OpenAI, which helps it build the KQL and understand the network environment. The tool's choice parameter is set to required. This forces OpenAI to respond with a tool call prompt management tools. This ensures you receive a structured JSON response rather than just conversational text. Let's dive deeper into the code and see how the system prompt tool selection dictionary and the tools list instructs the agent to select the right table and fields based on the user's request. In the previous segment, we saw that during the OpenAI function call, the parameter tool choice was set to required. That setting makes OpenAI use the tools list variable you define here to guide its response. That instruction is made explicit in the prompt management module through these two code blocks, the system prompt tool selection and the tools list variable. Inside the system prompt tool selection, under the heading Tool Usage Contract, we see the line, you may call exactly one tool, Query Log Analytics. You'll also find other mandatory rules. You must return a JSON object, never omit parameters, and only request fields listed for each table in the tool description. The tools list defines the Query Log Analytics tool used by the agent. Here, we're not writing a function in the traditional sense. Instead, we're defining a tool interface. Think of it as OpenAI's menu of abilities, where each tool is a menu item. Each menu item acts like an instruction card, explaining what action the AI can take and what data it can request. The tool gives OpenAI a list of available tables and explains how each might assist in the investigation. For example, since we are focused on unauthorized logins to the device wallet, we tell the AI that device logon events table contains logon activity against one or more servers. Once the AI identifies the correct table from the user's context, the field section specifies which values must be retrieved using that table. So far, we've seen how the prompt components make the agent more accurate and efficient, producing structured, data-driven results you can trust. To keep that performance consistent and contained, the agent also needs clear boundaries, rules that ensure predictable, compliant, and cost-effective behavior. This is where the guardrails component comes in. It enforces security, discipline, and cost control across every investigation. Now that we've defined what the guardrails are, let's take a closer look at how they're implemented in code and why they're so important to the agent's reliability and security. The Guardrails Python module has two configuration dictionaries and two validation functions. The first configuration dictionary, allow tables, deal with scope control. It contains a list of allowed tables and fields that the agent is permitted to use. This keeps the agent focused on the relevant telemetry and prevents it from requesting unsupported or sensitive data. For example, the domain field in the device logon events table may reveal the organization's domain naming conventions. Second guardrail configuration component deals with model governance, which enforces the use of approved AI models. It's important to note that not all AI models are the same. Different models charge different amounts for the number of tokens used. A token is a measurement of the amount of data that is sent to the agent as a request or received from the agent as an answer. The window is the amount of tokens the AI model can remember during a conversation. Max output tokens refer to the maximum number of tokens the model could generate in a single response. Think of it as the model's maximum reply length. Each OpenAI model operates under a different cost structure, measured in per 1 million tokens of input, cached input, and output. This pricing structure has real implications for how we design the agent's guardrails. Every investigation must balance costs against analytical depth, speed, and reliability. Larger models like GPT-5 deliver deeper analytical reasoning and a stronger factual grounding, which means they are less likely to produce hallucinations and can interpret more complex data relationships. However, these models also consume more tokens per query and therefore come at a higher operational cost. Smaller models, such as GTP-4o Mini, are faster and more cost-efficient, but they may lack the nuanced reasoning required for complex investigations. Looking at our brute force investigation on device wallet, the agent has chosen GTP-5 Mini to conduct the investigation. The token amounts are within the permitted guardrails values. It also estimates the cost of this investigation to be 0.002468 cents. In summary, guardrails give the agent structure and discipline, keeping every investigation accurate and controlled while preventing overreach or speculative results. The allow tables and allow modules list work together to protect accuracy, manage costs, and ensure the agent remains a credible and resilient cybersecurity assistant. We now explore the three core configuration components, the system prompt, the user prompt, and the guardrails, and seeing how each one contributes to the agent's accuracy, structure, and discipline. But there's one more element that ties everything together, and it doesn't exist in code at all. This final element is called contextual tuning. It's not just another line of Python code, it's a framework that drives the agent's intelligence, shaping how prompts are written, guardrails are enforced, and findings are interpreted. This slide highlights several points in the codebase where contextual tuning's influence is clearly visible. We can see this in the prompt component, the executor module, and the guardrails module. These examples show that contextual tuning isn't just a concept. It's the guiding framework that gives the agent its analytical discipline and real-world awareness. Think of contextual tuning like the NIST 800-61 framework. NIST 800-61 outlines how to respond to cybersecurity incidents, but it doesn't tell you exactly what commands to run. In the same way, contextual tuning provides the investigative mindset, the reasoning process that guides the agent's behavior across every component. Now that we're coming to the end of our discussion on the agent's configuration, let's go back to our brute force investigation with the device wallet. This time, however, let's remove three critical tables for brute force investigations from the query log analytics list in the prompt management module. Let's comment out references to the device network events table, the device logon events table, and the sign-in logs table. Now let's run the agent and enter the original question. Looking closely at the results returned by the AI agent, it's clear to see that we have very different results. The agent has chosen the next best table to query, device process events. While this does produce some legitimate threat IOCs, it totally misses the mark on what we're interested in investigating: unauthorized logon attempts. Furthermore, as can be seen in the section Potential Threat Number 3, the agent points to a lack of telemetry data in the device process events table as a reason why it cannot provide direct evidence of interactive logon attempts. For indicators of compromise, it states, none found in process lists specific to logon attempts. These results clearly demonstrate that without proper configuration, our AI agent is limited in its ability to offer any real help with our investigations. As I mentioned in the introduction, this video isn't about learning how to code your own SOC AI agent in Python. There are already powerful SOC AI products available commercially, so no company is going to hire you to build one from scratch. What truly matters is an understanding of how these systems think and operate, how they're configured, guided, and fine-tuned. That's what distinguishes an analyst who leads and shapes AI outcomes from one who merely uses it. Throughout this video, we've explored the core design of a SOC AI agent, its prompts, guardrails, and the contextual tuning framework that gives it intelligence and discipline. We've seen how your expertise as an analyst drives every part of the agent's reasoning process, shaping how it analyzes data, enforces security, and produces high-confidence, data-driven results. The takeaway is simple but powerful. You don't need to fear SOC AI agents. Instead, see their emergence as an opportunity to leverage and expand your knowledge, to integrate their capabilities into your investigations, and to become a more efficient and insightful cybersecurity professional. The future SOC AI agent won't replace the human analyst. It will amplify them. And the professionals who understand how to configure and guide and optimize these AI-driven tools will be the ones leading the next generation of threat hunters. So as you continue your journey, remember this. You don't have to compete with AI. You have to master it. Because mastery, not fear, is what defines the next era of cybersecurity. Hey, thanks so much for checking out my video. I appreciate your time and interest. If you found it helpful, please click that like button and share it with anyone who might benefit. You can also check out my cybersecurity portfolio to see some of my other projects. There's a lot more cool stuff in there. The link is below. And if you're thinking about getting into the cybersecurity field, definitely check out Josh Madakor's website, The Cyber Range. It's a fantastic place to start learning hands-on skills. Thanks again for watching, and I'll see you in the next video.